Hi everyone, welcome back. This is Dr. Cofield again, and this time we are going to look at reactions and how we can determine the limiting reactant. Why is that important? Because you don't always have all you need of every item, and so it's important that you can figure out exactly what you can produce with the materials that you have. So let's say that we have 5 moles of CO. It's not doing my pen again. I don't know why it does that. We have 5 moles of CO to start with. Okay. So we got 5 moles of CO and 8 moles of H2. So we've got 5 moles of this and 8 moles of that. So what does that tell me? That tells me that I may not be able to make all of 5 moles of my product, of my alcohol. All right, and so some of the things you can kind of do in your head maybe a little bit, but it's always better to do it based on the molar ratios. So, the moles of hydrogen, we've got 5 moles of CO, 2 moles of hydrogen for every 1 mole of CO. That means it would take 10 moles of hydrogen to completely react with the 5 moles of CO. Because we only have 8 moles of hydrogen, there's insufficient hydrogen to react with all the CO. Therefore, we say that the hydrogen is the limiting reactant and the CO is in excess, or it's the excess reactant. So to determine how much CO will be left over when the reaction is complete, we've got to first calculate how much CO will react with all 8 moles of H2. So if we look at moles of CO, we've got 8 moles of H2 by the molar ratio of CO to H2. So we'll be using up 5 moles of CO. Since we originally were told we had 5 moles of CO, but we're only going to consume 4 moles of CO, then we'll have 1 mole left over. That means that we have 1 mole excess CO, and all of the H2 will be used up. So how does that translate to a problem? Okay, so lots of words in this problem, so I'm going to work it on the actual next page. Alka-Seltzer tablets contain aspirin, sodium bicarb, and citric acid. When they come into contact with water, the sodium bicarbonate and the citric acid react to form carbon dioxide gas and other things. An Alka-Seltzer tablet contains 1.700 grams of sodium bicarbonate and 1 gram of citric acid. One more 0. Okay, for a single tablet, if we dissolve that in water, let's calculate the following. Which ingredient is the limiting reactant? Okay, so if I have, so what I do is I'm going to calculate how much, what are we making? CO2. How much CO2 we can make from each one of those first, okay? So the first one I had 1.700 grams of the sodium bicarbonate, and I had 1.00 grams of the citric acid, which is H3C6H5O7. All right, so I've got to see how much CO2 I could make. Now you can see the number of moles. I usually take it all the way to the grams just because that's just how I was taught to do it originally. Okay, so I got 1.700 grams of sodium bicarbonate. I'm going to go ahead and do my molar stuff. The 1 mole of the sodium bicarb is 84.01 grams of sodium bicarb. So that's how many grams is in 1 mole of sodium bicarbonate. So remember, I'm going over the molehill, so I've got to do my molar ratio. So for every mole of sodium bicarbonate, so I've got a ratio of 3 NaHCO3s to 3 CO2s. Okay, so that gets rid of moles, that gets rid of grams of sodium bicarbonate. So now I've got moles of CO2. And you can stop there for this initial thing if you want to. I usually just go ahead and, because I'm taking it to CO2, so there's in 1 mole of CO2, there's 12 plus 36, that's 44 grams of CO2. Okay, and so with 1.700 grams of sodium bicarbonate, I can make 0.890 grams of CO2. Now, you know, if I go too fast for you on this stuff, I should have mentioned this earlier, you can always slow me down. You can stop, you know, to catch up if you need to, if you want to go through and add up the NaHCO3 and the CO2, which is, you know, what I did. I just did it to save time, to go ahead and have it for you. All right, and so then I'm going to do the same thing with the citric acid. Citric acid weighs a little bit more. In 1 mole of that, if you will excuse me, I'm not going to write that citric acid every time until I get to the, it's 192.12 grams. And I'm just going to write citric acid on there. All right, and you'll know what I mean, citric acid. All right, and then I have to do the molar ratio again. Again, I'm doing CO2, so it's still 3 CO2s, but the citric acid is only 1 mole of citric acid. All right, and then again, I'm making CO2, so it's 44 grams of CO2 in every mole of CO2. And so when I do that math, I'm going to come up with 0.687 grams of CO2. Okay, so which one is my limiting reactant? All right, well, which one can I make the least amount of CO2? That would be the citric acid. Okay, I can only make that much. So even though I have 1.7 grams of sodium bicarbonate that would make 0.890 grams of CO2, I'm limited by the citric acid, so I can only make that much citric acid with those 2 ingredients in those quantities. So that tells me that the citric acid is my limiting reactant. What mass of the excess reactant is left over when the reaction is complete? Okay, so to figure this out, what I'm going to have to do is I'm going to come back to my CO2, so 0.687 grams of CO2. Okay, that's what I am going to make, right? 0.687 grams of CO2. What mass of the excess reactant? Okay, so that means I'm looking at the sodium bicarbonate because it is what is left over. So I do the same thing that I was doing up here, but I'm going to start with the amount of CO2 I know I can make. All right, and it's 44 grams in 1 mole. And so I'm looking at the sodium bicarbonate. So for every 1 mole, for every 3 moles of CO2, I'll have 3 moles of NaHCO3, and then times the 84.01 grams, because I got moles, 1 mole of NaHCO3. That's why, even though it's a pain to write these, okay, you've got to, because you got to make sure that you're getting rid of the right thing, okay? So, and see, I just found a mistake. What did I do wrong? I've got this one upside down, and I know that because I'm looking at my units. So I got to go back, and I'm not stopping this, I'm just going to show you, because this is what I would do if I was working it, that it should have been 44 grams of CO2, and I know better than that, in 1 mole of CO2. I wrote that backwards. So my grams didn't cancel, and so as soon as I started doing my canceling, I saw that I had done that wrong. And so if I'd been doing it as I went, I would have caught that sooner. So then moles of CO2 has to be on the bottom, moles of bicarb has to be on it, because I'm looking at how much excess I'm going to have, and my excess is the bicarbonate. So there's 84.01 grams of bicarbonate in 1 mole of bicarbonate, and so that's showing me that I'm going to use 1.312 grams of bicarbonate with this. So this is how much I'm going to use with the 0.687. So what is my excess? My excess is going to be whatever I had to begin with. If you remember from the original problem, was 1.700 grams minus the 1.312 grams that I'm going to use. That means that I'm going to have left over 0.388 grams in excess of sodium bicarbonate. Why is that important? Okay, well, say you're in a plant and you're doing this and you're not using grams, you're using tons. All right, and if you have that much per gram left over, then you calculate that up to tons. You're going to be costing your company a whole bunch of money. And so that's what they use these limiting reactant, excess reactant calculations for. In a mass balance, as an engineer, you'll see that done quite a bit. It's all about the money. All right, here's your practice to find the limiting reactant, the mass produced in this reaction. Okay, all right, that's it. And that's for limiting reactants. And so now that we can do limiting reactants, we're going to look at percent yield, which we have to use limiting reactants for. So we just keep building. And so the last part, the exciting climax, is going to be the reaction yield, comparing actual to theoretical yields.